Good afternoon. My name is Tobias Reichenbach. First of all, I would like to thank the organizers for organizing this virtual conference. I think it's a very exciting opportunity. So my group works on hearing, and recently we have begun to use transcranial current stimulation as a tool to investigate the neural mechanisms that are involved in sound processing. And today I want to share some of our recent findings with you. And to do that, I have prepared a short presentation that I want to show you in the following. It's been a while, probably for all of us, that we've been to a busy restaurant or pub, but I'm sure we still remember that these can be very noisy circumstances where it can be quite difficult to focus on a particular speaker due to all the surrounding distractor speakers. However, for healthy adults, it's actually relatively straightforward to tune out background noise. We are really very good at it, and to kind of keep talking to a particular person. But how does it actually work? How does the brain do it? That's what my group is working on. And to understand that, we might want to take a closer look at speech and what the building blocks actually are. So the shortest time scale, about 20 milliseconds, we have phonemes. So that time scale of 20 milliseconds corresponds roughly to the gamma range, 30 to 50 hertz, the lower gamma range. Then we have syllables that last a bit longer, like 50 to 100 milliseconds. That corresponds to the theta range. And then we have a rhythm set by words. These last 20 to 300 milliseconds. And that lies in the delta range, about 1 to 4 hertz. Now, a lot of research has shown that there is cortical activity in these different frequency ranges. And this activity on these oscillations entrain to the rhythm in speech that is set by phonemes, syllables, and words. And that seems to constitute mechanisms for speech processing. We still don't understand too well how exactly that works. There's a computational model developed by Alexander Hürfield a few years ago that works with a theta module that generates theta oscillations and the second module that generates gamma oscillations. And in this model, both modules receive sound input. The theta module then acts to parse speech into syllables, and that controls the output of the gamma module, and that then encodes the syllable identities. Transcranial alternating current stimulation, as we know, can modulate activity in the brain at different frequencies. Typically, people use frequencies between 1 to 50 hertz. The currents are very small, but in animal experiments, we nonetheless find that these small currents still are sufficient to modulate this oscillatory activity. Accordingly, we might speculate that transcranial alternating current stimulation might influence speech comprehension. And in 2018, there have indeed been a series of papers published on exactly this question. What the authors did is to present people with speech and noise. And at the same time, they also stimulated their auditory cortices using current stimulation. And the current stimulation was not just alternating at a single frequency, but it followed the speech envelope. So in other words, it had a broader frequency spectrum. The speech envelope in particular mimics the rhythm of words and syllables. So in particular, it encompasses the delta and theta frequencies that correspond to that rhythm set by words and syllables. By doing so, they found that this current stimulation did indeed influence the comprehension of speech and noise by a few percent, or maybe up to 1 dB in the sentence reception threshold. What we wondered then is, where exactly does that effect come from? I just said that the speech envelope contains frequencies both in the delta range and in the theta range. You can see that in panel C in a spectrum from a typical segment of speech. But these two frequency bands appear to play quite different roles in speech processing. In particular, the theta band appears to be more responsible for syllable parsing. The delta band follows more the word rate. Some people think it's related to higher level linguistic comprehension. So we wanted to investigate this question using current stimulation. We therefore presented people with sentences in noise. We also stimulated their temporal lobes using transcranial currents. And we used waveforms that were derived from the speech envelope, but filtered to lie either in the delta band or in the theta band. And so this gives the black waveforms that you see in panels D and E. So D is the delta band portion of the speech envelope, E is the theta band portion. Clearly, the theta band portion is faster because it's a faster timescale. What we then also did is to consider 6 different phase shifts. So we shifted the phase of these waveforms by 60 degree, 120 degree, 180 degree, 300 degree, and then 360 being back to the original, meaning no phase shift. And so these waveforms are shown in these thinner lines with these rainbow colors, and together they then fill out that space. We then measured the speech comprehension in percent at a fixed signal-to-noise ratio. That meant the speech comprehension was around 50 to 60%. And we looked at how that changed potentially due to the current stimulation at particular phases. Because we looked at phase shifts, we could use circular statistics to analyze the results. We then find that for the delta stimulation, there's no significant effect of the phase. It looks like at 60 degrees it's a little bit less, but it turns out it's actually insignificant. It's different for the theta band. For the theta band, we find that there's a significant modulation of speech and noise comprehension, in particular at the phase of 0 degree. Speech comprehension is maximal at around 60%, and at a phase of 180 to 240 degrees, it's minimal at around 55%. We can fit a sinusoidal function to that, and we see that that fits the mean values shown with these circles indeed very well. So this is really interesting for the speech processing perspective because it clearly shows that the alternating current stimulation acts on the theta band portion, but not on the delta band portion of the neural machinery. We then also looked at the issue of subject-to-subject variability. So previous work had suggested that the effects of the current stimulation on speech comprehension might be quite different from one subject to another one. And we looked at that in our data. And to do that, we looked for every subject, what was the best phase, meaning at what phase did the subject have the highest speech comprehension. So we call this the best phase, or B, in panel A and B. And we then measured the phases relative to this best phase. That's why we then have the best phase plus 60 degree, plus 120 degree, and so on. Interestingly enough, then, both for the delta band and for the theta band portion, we find that there's no significant effect of the phase anymore. Now, for the delta band, that's not surprising because there was no significant effect before either. For the theta band, it's a bit more surprising because we had a significant effect that now has disappeared. So what that suggests is that this fact of choosing the best phase actually makes the data noisier rather than less noisy. And that suggests that the best phase is probably actually relatively consistent across subjects. To look at it from a different angle, we then looked at the distribution of the best phases across the subjects in a histogram that's shown in panels C and D. For the delta phase, we find that most people have a best phase of 180 degree, very few a best phase at 60 degree, but actually the effects are not significant. It's not significantly different from a uniform distribution. Again, that's not surprising because there's no significant effect that we observed so far. So also it's not surprising that there's no significant distribution of these best phases. Again, it's very different for the theta portion. There we find that most people have a best phase of 0 degree, and that effect or that peak is highly significant. It's very different from a uniform distribution. So that shows what we said before, namely that there's a consistent best phase across subjects, and that best phase is 0 degree, meaning no phase shift between the current waveform and the speech envelope. That's when people do best. We also looked at if the stimulation using the theta band and no phase shift can actually enhance speech comprehension beyond charm stimulation. So far, we always compared different phases to each other, and we showed for the theta band that yes, there is an impact of the phase, but that doesn't mean that you actually improve. It could just mean it's always getting worse due to the stimulation. But this data that I show on this slide actually shows that if we stimulate with a theta band portion of the speech envelope without a phase shift, then actually we improve significantly compared to charm stimulation, and also significantly as compared to if we take an unrelated speech envelope in either the delta or the theta band portion. So that shows that not just can we influence speech comprehension using the current stimulation, but we can actually improve it. And that might have implications for treating hearing impairments, for instance. Finally, we looked at a second parameter that is important for the current stimulation, namely at the temporal delay, meaning the delay between the current waveform and the speech signal. For that, we used a range of delays going from minus 430 milliseconds, meaning the current waveform precedes the audio signal, to plus 400 milliseconds, meaning there's quite a delay between the current and the audio signal. And we use the delays based on the autocorrelation of the speech envelope to pick out maxima and minima, with the idea to get contrast between different temporal delays. What we found is that very consistently across subjects, almost all subjects had the best delay at 0 milliseconds, meaning for almost all subjects, no delay gave the largest speech comprehension. And if you look then at the actual comprehension scores, again, we find that at no delay and also at the delay of 90 milliseconds, we find a significantly larger comprehension as compared to charm stimulation. Again, going back to what we just said, we can actually improve speech comprehension by using the theta band portion of the speech envelope and having no delay and no phase shift. I want to conclude by just mentioning that we are also working on a computational model of these effects. This builds on the work by Alexander Hühnerfjell that I mentioned before on the spiking neural networks using a theta module and a gamma module. And we now use that to simulate speech and noise comprehension. And the results are quite similar in some ways to human performance. And now we also use it to simulate current stimulation. And I can hopefully update you on these results in the meeting next year. With that, I want to conclude by summarizing the main points for our findings. Importantly, we found that transcranial alternating current stimulation with the speech envelope can actually enhance speech comprehension and noise. The effects result from the theta band portion, but not from the delta band portion of the speech envelope. And the enhancement is largest when there's no phase shift and also when there's no time delay between the current signal and the speech stimulus. Interestingly and importantly, I think this effect seems to be fairly consistent across subjects. With that, I want to thank the people in my group who did the work, in particular Shabnam Kadir, Mahmoud Keshavarzi, and Mikolai Kegler, as well as funding agencies. And thank you very much for your attention.